6.08 times 10 to the minus 6. And you say, oh, look at that, base dissociation, that must be the hydroxide ion concentration. What do I need? I'm plotting pH. So I need the hydrogen ion. I'm going to get POH because I have the number here. And I can subtract easily. So it says POH 5.22. And I subtract 14. Whoops. Now I subtract it correctly. pH 8.78, just like somebody predicted, it's slightly basic. So here's my equivalence point. 7, here's 7, 8.78, so it's right in here for my equivalence point. I'll use a little text. Notice it's closer to where the phenolphthalein came. So phenolphthalein might be a better indicator for this particular titration. Okay. What about the half equivalence point?
It would be the Ka, right?
Yeah, because we're working with a buffer solution. But there's something even more interesting about it. I don't know if I'm catching a cold. It's my allergy from these tiles again. Or, holidays that we work on the system. Okay, so coming back to this thing, I'm doing my half equivalence point. And there's something really interesting about the half equivalence point. What it means is I've titrated half of this, or half of this. Whoops, I'm the wrong problem here. I've titrated half of this. So half of it is this form, half of it's this form. Right? Because I've converted half of my acid to the salt. That's why we call it half equivalence point. We've gone halfway. And the reason I wanted to do that, I say, oh, this number is equal to this number at the half equivalence point. And so now pH is equal to pKa. Oh, wow. But I'm just punching the wrong button here. Much of a hurry. pH is 4.74 once I hit the right buttons. So the half equivalence point in these weak acid base titration, weak acid strong base, or even strong base weak acid, can be calculated directly from the K. When I put this on the quiz, it's only worth 1 or 2 points. But notice one of the things here, 4, 7. First of all, it doesn't start off as low, but but also it's going up faster. Here it sort of stayed pretty constant all the way across here. And it does something funny in here. They always either leave this blank or they do a little thing like this. And it starts going up like that. And maybe I made it too fast. Like that. And I'll do 30 milliliters again. But right in here, let me first of all point out, because this is what I want to look at. The starting point is the simple acid-base problem. The equivalence point is what? The hydrolysis problem. In between here and here, what type of problem do you have?
Buffer.
Buffer problem. So the titration curve has all three different types of equilibrium problems, and you know which one you have to do at which place, as long as you remember to calculate the volume to get to the equivalence point. Okay. Because then you can look at whatever volumes I asked you to calculate, and that immediately tells you which of the three types of calculations you're going to do. So I'll do one buffer point, and I'll pick 30 milliliters just for comparison purposes. And I already did the stoichiometry for 30 milliliters. There was 1 millimole of weak acid unreacted. I'll just write this thing. As I So basically, there's, we started off with 4, we added 30 times 0.1, and over here, we got what? 3 millimoles of the salt. In other words, we used up 3 millimoles of the acid, we used up 3 millimoles of the hydroxide, which is the limiting reagent, and we produced 3 millimoles of the salt. So at equilibrium, 1 millimole, 3 millimoles. I don't need any of this other stuff because I've already talked about this, so it's board space. So I'm doing the calculation for the buffer solution now. And I have my amounts here. This is my I. Oops, I'm wrong. I still have, that's my stoichiometry. Now what I have to do is my dissociation reaction. My initial here is 1.0. I've added 30 milliliters to the 20, 50. The hydrogen ion, 0. A minus, 50. Okay. The change, notice, and I did, we're at this problem right here. I have X for the hydrogen ion. I have C prime plus X for the conjugate base. And I have C0 minus X for the acid. I have my buffer problem. So I'm going to just write that now. I'm going to say Ka. Because I'm still talking about a weak acid. And as I said, when we do buffers, we almost always do it by approximation. For this class, always, I guess. And notice in this way of setting it up, as long as I don't make a mistake with the volumes, they're gonna cancel out. I didn't make a mistake, so I can cancel them out. If I make a mistake, they still cancel out, but you have to be careful that you make the right kind of mistakes. So I'm just gonna cancel them out. And so now you have so I get pH. pH is 5.22. You show me this to be the right number for the pH, I'll believe you didn't make a math mistake or whatever. If you show me the wrong answer for pH, so then I have to do something. 5.22. Still drifting up this way, there didn't go quite far enough. There's my equivalence point, it's gonna do this, it's more shallow going up through here. What happens after I pass the equivalence point? And I add, which problem did I do? I added 41 milliliters of NaOH. This curve stays the same, because now all I have is excess strong base. That's what determines the pOH, and therefore the pH also. So once I get to the equivalence point, this part of the curve stays the same. Okay. My curve doesn't look that good. I think they do more of it like this. So notice one of the things, this part of the curve doesn't have a sharp gradient, as they say, as my strong acid, but it's a weak acid, strong base sort of thing. It has more of a shallowness to it. So this is sort of the titration curve you get from weak acid with a strong base. Polyprotic acids, how does that work?